Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Question 23 states that neutrons released by a fission reaction must be slowed by collisions with the moderator nuclei before the neutrons can cause further fissions. So if we suppose that a 1.5 MeV neutron, which I call Q initial here, leaves each collision with 65% of its incident energy, how many collisions are required to reduce the neutron's energy to at least 0.04 eV, which is the energy of a thermal neutron? Okay, so these are our couple of statements here. We're given the initial energy of our neutron, and we want to know how many times does it have to hit something, in which every time it hits, it loses or it only maintains 65% of its energy upon hitting. How many times does it have to collide, to go from 1.5 MeV to 0.04 eV, electron volts. So if we model that, so if we say Q initial is 1.5. Let me see. I just want to show a model of this, so I'll leave it as this for now. So that's 1.5 MeV. So once it makes one collision, we can say it has 1.5 MeV times the percent ratio that it maintains, which is 65%. And again, upon the second collision, it has 1.5 MeV times what it had before colliding. And again, with another collision, another 0.65 is maintained, which we could represent this Q2 to be 1.5 MeV, or actually maybe more appropriate. I'll leave this as Q naught, the original energy, times 0.65 squared, right? Because you're multiplying 0.65 twice. So that means if we want to find the energy on our let's just call it, I don't know, mth collision, that simply can be modeled by the initial energy multiplied by 0.65 to the power of m. So m here, I guess I could use n for number of collisions. That was a little silly, but that's okay. So this is our relationship that we have where the energy of our neutron after m collisions is given by this value, right? So in this scenario, we want to solve for what m is. Well, if we know finally our Q final after we hit m times, actually we know that to be 0.040 eV, and we know Q naught, we can rearrange this equation to solve for what m would be. So we'll take the ratio, so that's Qm, which I'm calling Q final here, over Q naught, our initial, equals 0.65 m to the power of m. Well, that means to solve for m, we have to take the natural logarithm of both sides of our equation. So that'd be Qm over Q naught. That's equivalent to the natural logarithm of 0.65 to the power, to the power of m. Which, if you remember, the natural logarithm of something to the power comes down out front. And so I'll switch both sides. I'll switch these so I have my m on my left side. So we have m times the natural logarithm of 0.65 equals the natural logarithm of the ratios of energies, Qm over Q naught. So finally, we can find the number of collisions to be the natural logarithm of ratio of energies divided by natural logarithm of 0.65. So you can simplify these two natural logarithm expressions. I'm just going to leave it as is just to show the difference. And we find that this m value would be 40.8, but we can only have an integer value of collisions. So if we had 40, we'd be under So because the question does specifically mention it in a way where the neutron's energy must be at least 0.04 eV, that will only occur upon the 41st collision. So there you go. So using the information provided to us, we were able to model an equation to represent what's happening per collision, and simply we rearrange that equation to find the number of collisions.